Hello, my dear students. This is the part second of lecture 5, outer measure and measurable sets. So, in this lecture, we are going to through the remarkable properties of measurable sets. First, we will show that the class of measurable sets is sigma algebra, and then we will show that if we restrict to the function outer measure to the class of measurable sets, it will be the measure on that class. So first of all, we will show that the class of measurable sets is a sigma algebra. So the class of throughout this lecture series, the class of measurable sets will be denoted by lambda. So that's a notation for class of measurable sets. It's a subset of power set of X. So let's prove the following theorem. The class lambda of all measurable sets is sigma algebra. Proof. So this what's lambda? Lambda is a class of measurable sets. So lambda is this set, and lambda it's those subsets of X satisfy the following property: mu of A is equal to mu of A intersection E plus mu of A intersection E complement for every subset A of X. That's the lambda, and we will show that this lambda is sigma algebra. So let's do the first property. First property is that the empty set should be there. Since outer measure of phi is 0 by definition of outer measure, so that means phi is a null set, and also we have proved that in the previous lecture that every null set is measurable, and this empty set is a null set, therefore it's measurable. So therefore phi belongs to lambda. Phi belongs to lambda. That's the first property of sigma algebra. So in the next property, we will show that this class, this collection of measurable sets is closed under finite union. So next property, we show that lambda is closed under finite union so let E1 comma E2 belongs to lambda. We show that E1 union E2 is also the member of lambda, and let E be equal to the union E1 union E2. It's the same as E1 union E2 minus E1. Okay. Now, mu of E, which is always less or equal to mu of A intersection E plus mu of A intersection E complement. And let's write this E as E1 union E2 minus E1. This is equal to mu of A intersection E is equal to E1 union E2 minus E1. E1 union E2 minus E1 can be written as E2 intersection E1 complement. Alright, plus mu of that set, it's A intersection E. Let's write this E is equal to E1 union E2. It's E1 union E2 complement. So now we apply here distributive law, and here we apply the De Morgan's law. So that implies mu of A is less or equal to mu of A intersection E plus mu of A intersection E complement, and here it's equal to mu of A intersection E1 union A intersection E2 intersection E1 complement, intersection E2 intersection E1 complement, plus this one plus mu of A intersection, this will be E1 complement intersection E2 complement, E1 complement intersection E2 complement. Now we apply here sigma sub additive property of outer measure, because mu is an outer measure, it's less or equal to mu of A intersection E1 plus mu of that set. So I will interchange these two sets, E2 and E1 complement. It's mu of A intersection E1 complement intersection E2, and plus this one mu of A intersection E1 complement intersection E2 complement. Now look at this. Since E2 is measurable, therefore mu of A intersection E2 plus mu of A intersection E2 complement is equal to mu of A for every subset A of X. So in particular, it's true for A intersection E1 complement also. So that means mu of A intersection E1 complement intersection E2 plus mu of A intersection E1 complement intersection E2 complement is equal to mu of A intersection E1 complement. So it's equal to mu of A intersection E1 plus mu of A intersection mu of this is mu of A intersection E1 okay, plus mu of A intersection E2 intersection E1 complement, and here we have E1 complement. Okay, it's mu of A intersection E1 complement. Okay, it's fine. By measurability of E2, by measurability of E2. Okay, so what do we mean by measurability of E2? Means mu of A intersection E2 plus mu of A intersection E2 complement is equal to mu of A for every subset A of X. So this is the measurability of E2. E2 is measurable, therefore it satisfies this property for every subset A of X. So here we replace that subset A of X by A intersection E1 complement. So this A intersection E1 complement is also the subset of X. So therefore if we replace A by A intersection E1 complement, this sum will be equal to mu of A intersection E1 complement. Now here we apply the measurability of E1. So mu of A intersection E1 plus mu of A intersection E1 complement is equal to mu of E. Is equal to mu of A, because by measurability of E1. So therefore mu of A is less or equal to mu of A intersection E plus mu of A intersection E complement, which is less or equal to mu of E. So that means mu of A is equal to mu of A intersection E plus mu of A intersection E complement. So therefore mu of A is equal to mu of A intersection E plus mu of A intersection E complement. So that proves E is measurable, which implies E, which is equal to E1 union E2, also belongs to lambda. So therefore lambda is closed with respect to finite unions. So this also proves it's closed with respect to finite intersection, because we know that whenever E1 and E2 belongs to lambda, then their complement is also lambda. It's already discussed. Also since E1 complement comma E2 complement, it also belongs to lambda. So therefore E1 intersection E2, I will show that this also is the member of lambda. It's equal to E1 complement union E2 complement whole complement. This E1 complement is in lambda, E2 complement is in lambda, because lambda is closed under complementation, and as already proved that lambda is closed under finite unions, therefore their union E1 complement union E2 complement is also the member of lambda. So this union is the member of lambda. And again, lambda is closed under complementation, therefore its complement also is the member of lambda. So it's the member of lambda. So thus we have proved that thus lambda is closed under finite unions and finite intersections. So next we'll see that lambda is also closed under difference of sets. So if E1 comma E2 belongs to lambda, then we will see that their difference, set difference, is also the member of lambda, and it's equal to E1 intersection E2 complement. Now look at this. E1 is a member of lambda, E2 is a member of lambda, therefore E2 complement is also the member of lambda. So that means both E1 and E2 complement, they are both the members of lambda. And we already proved that lambda is closed under finite intersections, therefore their intersection is also the member of lambda. It belongs to lambda. So thus lambda is closed under difference. So this proves that lambda is an algebra. So therefore lambda is an algebra. Therefore lambda is an algebra. But we need to show that lambda is a sigma algebra. So and we know that a sigma algebra is an algebra which is closed under countable union. So now we prove that lambda is closed under countable union. Now we prove that lambda is closed under countable unions. So for this we take a sequence of sets in lambda, and we'll show that their union is also the member of lambda. So let's take that sequence. Let En, they are the members of lambda. We show that the union En runs from 1 to infinity, which we'll denote by E, is also the member of lambda. This is what we have to prove. Its union is also the member of lambda. To prove this, we construct the new sequence, say Gn. Let's define Gn. Which is a disjoint sequence. Define Gn, which is equal to En minus union I runs from 1 to n minus 1 Ei. It's a disjoint G1, G2. It's a disjoint sequence. It's already discussed. But the interesting property is that this Gn is also the member of lambda. Why? Because En is a member of lambda. I runs from 1 to n minus 1. They are also the members of lambda, and we know that lambda is closed under finite union. Therefore, this union is also the member of lambda. En is the member of lambda, and we also know that the difference lambda is closed under difference. So therefore, the difference of two members of lambda must be the member of lambda. So that means this difference is the member of lambda for all n greater or equal to 1. And it's a disjoint sequence. So thus Gn is a disjoint sequence in lambda. It's a disjoint sequence in lambda. So now we define Gn is a disjoint sequence in lambda, and also one more important property, and this is same as union Gn, and also wanted because union Gn is same as union En actually. It's the same union. It's the same. Now we define. Now let's define. Now define Fn, which is the union of n G's. It's equal to union Gi I runs from 1 to n. Then you can see that this union Fn n runs from 1 to infinity is same as union Gn n runs from 1 to infinity, which is same as union En n runs from 1 to infinity, and that's equal to E. So all the unions are same. And also, we see that this Fn, which is the finite union of the finite GIs, it will be subset of the union of all GIs, and that's equal to E. So Fn is subset of E for all n greater or equal to 1. So and these Fn's, they are also measurable sets, because GNs are all measurable sets. It is a disjoint sequence of measurable set, disjoint sequence of the members of lambda. Lambda means a class of measurable sets. So this G1 is measurable, G2 is measurable. They are all measurable. They are all the members of lambda, and lambda is closed under finite union. Therefore, Fn is also the member of lambda. So Fn, they are the members of lambda. So also this Fn, it belongs to lambda for all n greater or equal to 1. Okay, now we prove the measurability of E. Measurability of E, which is the union of E's. Now, mu of A, it's equal to, since Fn is measurable, it's equal to mu of A intersection Fn plus mu of A intersection Fn complement, as Fn belongs to lambda. And that's equal to, now look at this, Fn is subset of E, so that means E complement is subset of Fn complement. E complement is a subset of Fn complement. E complement is subset of Fn. That Fn complement contains E complement. Fn complement is bigger than E complement. So that means measure of this set A intersection Fn complement will be greater or equal to measure of A intersection E complement by monotone property of outer measure. So it's greater or equal to mu of A intersection Fn plus mu of A intersection E complement. Let's write here as E complement is subset of Fn complement. So E complement, Fn complement is bigger than E complement. So that measure of Fn complement will be greater or equal to measure of E complement. Now we expand this one, it's equal to mu of A intersection Fn. What's Fn? Fn is union Gi, I runs from 1 to n plus this one, mu of A intersection E complement. And that's equal to mu of union I runs from 1 to n A intersection Gi plus mu of A intersection E complement. Now here, and we have already proved in previous lecture that whenever A1, A2, En are disjoint measurable sets, then mu of union I runs from 1 to n A intersection Ei is equal to summation I runs from 1 to n mu of A intersection Ei. And here Gi's are measurable and they are also disjoint. So therefore mu of union I runs from 1 to n A intersection Gi will be equal to summation I runs from 1 to n mu of A intersection Gi. This is equal to summation I runs from 1 to n mu of A intersection Gi, it's already proved, plus mu of A intersection E complement. So this is true for actually all n greater or equal to 1. It's true for all n greater or equal to 1. Now letting n approaching to infinity, so this is actually here mu of A is greater or equal to this. So letting n approaching to infinity, this gives mu of A is greater or equal to summation I runs from 1 to infinity mu of A intersection Gi plus mu of A intersection E complement. And this one it's greater or equal to mu of union I runs from 1 to infinity A intersection Gi by sub-additive property of mu, because mu is outer measure, that means mu of union will be less or equal to summation I runs from 1 to infinity mu of A intersection Gi plus mu of A intersection E complement by sub additive property of mu, by some additive property of mu. So now this one it's equal to mu of A intersection union I runs from 1 to infinity gi plus mu of A intersection E complement, and that's equal to mu of A intersection E, because union gi I runs from 1 to infinity is E, plus mu of A intersection E complement. So mu of A is greater or equal to this, but mu of A is always less or equal to this. That inequality always hold. So therefore mu of A is equal to this sum. So you have proved that mu of A is greater or equal to this, but mu of A is always less or equal to mu of A intersection E plus mu of A intersection E complement. So combining these two inequalities, therefore mu of A is equal to mu of A intersection E plus mu of A intersection E complement. So this proves the theorem. This proves the theorem that E is measurable. E is measurable. So this proves that E is measurable. So this implies that E belongs to lambda. So thus lambda is closed under countable union. So therefore lambda is sigma algebra. It is sigma algebra. Next theorem is a very important theorem. It's a remarkable theorem because in this theorem we are going to prove that when we restrict outer measure to this class lambda, it will turns out to be major. So that's we are going to prove that x lambda mu is a major space. So this is not major space in general. X power set of x mu. It's not major because mu is not sigma L2. But we are going to prove that when we restricted this mu to lambda, it will be a major. So that means x lambda mu will be a major space. That we are going to prove in next theorem. So what's next theorem? Next theorem is x lambda mu, and mu is an outer measure, is a major space. So that is mu restricted to lambda is a major. So proof is very simple, not too difficult. It's straightforward. It's a straightforward proof. So let's take any digits we can say lambda, digits we can say en. We will show that mu of union en is equal to summation of sum of mu of e and s. So let's take digits. So we can let en be any disjoint sequence in lambda, such that union is in lambda. That's already proved. Union is in lambda, so we don't need to write it here. We show that mu of union En n runs from 1 to infinity is equal to summation n runs from 1 to infinity mu of En. So one inequality is trivial by sigma additivity of mu, because mu is an outer measure. We have this mu of union En runs from 1 to infinity. It's always less or equal to summation n runs from it's by definition of outer measure mu of En. So now we prove reverse inequality. So to prove reverse inequality, let's take let n be any natural number. Then we have proved that this summation I runs from 1 to n mu of ei is same as union I runs from 1 to n ei, because outer measure it's mu of that disjoint union, finite disjoint union is equal to summation I runs from 1 to n mu of ei. It's already proved, I think in the previous lecture we have proved this result for a finite union. This holds, and this is less or equal to mu of union n runs from 1 to infinity. If I will take all the ei's infinite union, this is less or equal because mu is monotone. This union is subset of this infinite union, so mu of that finite union will be less or equal to mu of the infinite union. So letting apply and approaching to infinity, this gives summation I runs from 1 to infinity mu of ei is less or equal to mu of union n runs from 1 to infinity En. So that proves the reverse inequality. Thus mu of union n runs from 1 to infinity En is equal to summation n runs from 1 to infinity mu of En. So therefore mu is major, and hence x as mu is a major space. So in next theorem we will show that